ওকে, আজকে ক্লাসটা শুরু করছি। তাহলে স্ক্রিনটা শেয়ার হলে একটুখানি আমাকে বলো।
Yes, ma'am. Share it.
Okay. Okay. So today we are going to explore the counterpart of DAC, that is ADC, analog to digital converter. We have already seen that what are the significances of these ADC and DAC and where exactly we need those two blocks in the whole system. So here, just after the output of the transducer, we need this ADC. Why? Because transducer actually translates the physical parameter into the corresponding electrical one, which we can actually measure. But still, that electrical signal remains analog. So for the sake of the analysis, for the sake of the simplicity of the analysis, we now want to shift from analog to digital domain, and that is why we need to convert that analog signal into the corresponding digital one. So here as you can see, this is the block diagram of a typical ADC, analog input, and at the output we are getting the corresponding digital function. So here, how do we know that it is working as an ADC? Obviously, when the digital output is proportional to the analog input, that is, it is connected through some proportionality constant. That constant can be the internal gain of this system and whatever, some other also. So basically the relation is the digital output is proportional to what has been given in the input, that is the analog input. Now basically there are 5 types of ADCs. One is parallel comparator type ADC. Alternatively, it is called flash ADC. Why? We will see that. Then there is counter type ADC, or alternatively that is called single slope ADC. Next is coming tracking type ADC, then successive approximation type ADC, and last but not the least, the dual slope type ADC. So we are now going to explore these one by one. At first, let us see what do we mean by this parallel comparator ADC. Now from this name, we can actually say that it has to do something with comparison, because comparators are being used. And why parallel? Maybe a number of comparison is done parallel. So that is why the name parallel comparator ADC. And here at the output, this is the circuit schematic of typical parallel comparator ADC. And in the output, we are seeing that whatever be the analog signal, we are getting a 3-bit digital signal as output. So it is called as a 3-bit ADC. Now here you can see that these 7 op-amp like structure, basically these are the comparators. What are comparators? Comparators are nothing but the op-amp connected in open loop conversion. So there is no feedback from output to input, as it was in the case of a general or an ordinary op-amp. Here it is working as an comparator. That is, it will compare the voltages at its non-inverting terminal and its inverting terminal. So whatever be the voltage here and whatever be the voltage here, the output will actually compare these two. Now suppose the positive terminal voltage is greater than that of the inverting terminal. Positive or non-inverting terminal voltage has got a greater value compared to the inverting terminal voltage. In that case, it will produce a 1 output. And in case the inverting terminal is greater than that of the positive terminal's voltage or non-inverting terminal's voltage, then the output will be 0. So you can see over here, this is an op-amp. Suppose this is VA, suppose this is VB, and this one is output. So when VA is greater than VB, the output will produce a 1. And when VB is greater than VA, the output will produce a 0. So basically what is doing, it is actually comparing two analog voltages, but at the output it is either giving 1 or it is giving 0. So it is producing a digital output. So in one way we can see that a single comparator, we may say that it is as if converting an analog signal into a digital one. Although it is not converting exactly the analog signal, but it is actually based on the value of these two voltages, it is producing an digital output. So here in this present case, there is a V reference, and this V reference is actually connected to the inverting terminal of each of these comparators through some resistors. Now from here, one input is taken from this point, one input is taken from this point, and so on. So basically what we are doing, we are creating a voltage divider circuit. See, in each node, the voltage has been divided depending on the value of the R. So here from this figure, we can say that we have gotten a 7 equally spaced reference voltages. And here, suppose it is V reference 7, here V reference 6, V reference 5, etc. Now, if we want to calculate the voltage or the reference voltage at these points, we can simply say that for this one, what would be the voltage at this point? Simple, it is the drop against this R, this resistor. So if we calculate it, we will actually get, it will be V reference divided by 8, because the total number of resistance here 1, 2, 3, 4, 5, 6, 7, 8, and will be V reference divided by total resistance into R. This R and R will be cancelled out, and at this point we will get the V reference by 8. Here this is the voltage. Similarly, if we want to calculate the reference voltage in this stage, at this point, again, same way, another voltage divider circuit, but here that will be 2R, because it will be the voltage drop against this R plus R, this total resistance. And R will get cancelled. It will be something like 2V reference by 8. So in this way, if we move upwards, in upward direction, the voltage, the reference voltage value will be something like 2V reference by 8, then 3V reference by 8, 4 reference by 8. Ultimately, it will go here 7V reference by 8. So here 7 equally spaced reference voltages have been created. Now, the analog voltage, which we want to convert into its corresponding digital circuit, is connected to the non-inverting terminal of each op-amps or each comparator. So, depending on the magnitude of this V in, basically what is happening, for each comparator, this V in value is getting compared with the corresponding voltage at the non-inverting terminal, which are the reference voltage at that terminal that we have just compared. So total V reference have been actually divided into 7 such values, 7 such ranges. This one, here it is V reference by 8. So here V in is getting compared with V reference by 8. If V in is greater than V reference by 8, then the output will be 1. If V in is less than V reference by 8, the output will be 0. Similarly, if V in is greater than 2V reference by 8, the output will be 1. V reference, if it is less than it, the output will be 0. Suppose V reference, we are considering an example, suppose V reference is equal to 8 volt. So here it will be 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, and 7 volt. So for this, suppose V in has got now a value of 2.1 volt. Suppose. So what is happening? The 2.1 volt, when it is getting compared with 1 volt, it is greater than that of the 1 volt. So the output will be 1. Here it is 1. Now in this stage, for this comparator, 2.1 volt is still greater than 2 volt, which is the reference voltage here. So again the output will be 1 for this comparator. Here 3 volt. Now 3 volt is greater than 2.1 volt. So here the inverting terminal voltage is basically greater than the non-inverting terminal voltage. So at the output we are getting 0. Here also obviously if 3 is greater than the input voltage, then 4, 5, 6, 7, all these voltages will be greater than that of the input voltages. So the output of these comparators, that is from the third comparator to the last one, the output will be 0. So the corresponding digital signal that have been created is 1, 1, 0, 0, 0, 0, 0. This one is LSB and this one is LSB. Now this 7 output of these comparators, they are fed to a latch. Latch is nothing but it is holding this value, and with the application of clock or latch enabling signal, it will transfer the value from its input to output. Now here another thing is being used, that is what we call as a priority encoder. Now basically what is the job of this particular block? Forget about priority. Suppose it is an encoder, simply encoder, and the output here is 3-bit. So it has to be programmed in such a way so that all these 8 combinations here, this encoder is grounded, because 3 output means 2 to the power 3, total 8 number of combinations should be at the input, and here we are getting the 7 combinations. So here the LSB is grounded and the 7 combinations is connected like this manner. So from the second bit, or if this is the 0th bit, then from the first bit to the LSB, it is connected like this. So the job of this block, it actually encodes this entire thing in such a way so that it can produce the corresponding digital output. Now for this particular case, a priority encoder have been used. Now what is a priority encoder? Priority encoder means something to do with the priority. So here at the input, we have gotten total 8 number of input lines. Now each of these bits or each of these lines are assigned a certain priority. And interestingly, if we move from the LSB or lower significant bit to MSB, that is the most significant bit, the least significant bit to the most significant bit, the priority increases bit by bit. So LSB has got the least priority and MSB has got the most priority. Now what it has to do with the entire coding? Here this priority encoder works in such a way that it will search for the binary value 1. It will search for 1, and it will actually, suppose it has gotten combination of 0, suppose it has like 0 0 1 1 0 0 1 1 0 0 0, that is here it is 0, then 0 0 1 1 0 0. So it will search for this value 1. Here 2 bits has got the value 1. It will consider that bit which has got the highest priority. So out of these two, this one has got the highest priority because it is towards MSB. So it will consider this one, and at the output it will convert, or it will form the digital signal corresponds to this bit. So let us see the example over here. Now this comparator, here it is actually signifying the range, that is 0 to V reference by 8. What do we mean by that? It means that the VE, which is getting compared with this non-inverting, with this inverting terminal, and the inverting terminal has got the maximum value of V reference by 8. So until and unless it crosses this V reference by 8, the output of it will remain 0. So this signifies the range, that is 0 to V reference by 8. V in is falling here. Now in the second comparator, it is getting compared with this 2V reference by 8. So basically it means here it should be greater than this V reference by 8 but less than this V reference by 2. Once it crosses this 2V reference by 8, the output of this will become 1. So this one actually signifies the range, that is V reference by 8 to 2V reference by 8. Similarly, if we move on upward up to the last bit, it will actually define the range that varies from 7V reference by 8 to V reference or 8V reference by 8. That is when it crosses this one or becomes equal to this one, the output will be 1. Now, based on this A, B, C, D, E, F, G, the table is written like this. And this H is introduced here as the least significant bit of this priority encoder. So here you see, if all the values of this is producing 0, that is, this V in is less than V reference by 8, falling in the first range. So no 1 is here. So the output will be 0, 0, 0. If in this case, if the lower significant bit becomes 1, if it is set to 1, then also it will be 0, 0, 0. Because it is the 0th bit. So the corresponding digital equivalent of this 0th bit will be 0, 0, 0. But for the sake of instead of using an extra power supply, that will be something hazardous. So that is why it is simply connected to ground for the simplicity of this circuit. So it is 0. Now if V input is greater than V reference by 8, that is, this one is 1, but it is less than 2V reference by 8, that is, this F output is 0. The output would be 0, 0, 0, 0 up to this 1. And here, in place of H, we are putting a don't care condition, because we don't care whether it is its value is 1 or 0, because it hasn't got the highest priority out of these two bits. Here G value is 1, and it is the highest priority bits out of the bits which have gotten 1 value. So here for this particular combination, it is the 1th bit or first bit. So the corresponding digital signal will be 0, 0, 1. Similarly, when V in is greater than 2V reference by 8, these two, G and F, will be 1, 1, but E will be 0. So here now, F is becoming 1. We don't care what is the value of G and obviously H. It may be 1, maybe 0. We don't care. Why don't we care? Because G has got lesser priority compared to F. Now F is 1. F has got the highest priority among these two. So we will consider F. And what is the corresponding digital signal for that? It is 0, 1, 0. So in this way, if we proceed like this, for this value, for this range, for this range, for this range, ultimately for last value, that is the most significant bit here, is 1. So the corresponding digital, this is the 7th bit. If this is the 0th bit, this is the 7th bit. So the corresponding digital signal here we are getting as 1, 1, 1. When this one is 1, we don't care whether these bits has got the value of 1 or 0. So that is why we are putting a don't care conditions here. But actually, if you see the circuit outputs, when most significant bits is 1, then obviously all these bits, all this output of these comparators are already 1, because in this case the V in is actually falling in the range. It is greater than 7 V reference by 8, but less than 8 V reference by 8 or V reference. So it is falling in the final range. So obviously this V in will automatically be greater than all these reference values also. So this is how a priority encoder works, and in this circuit it is actually converting the corresponding analog voltage into its digital one. So this is how the parallel comparator ADC is working. See here, the comparison is done for all these 7 comparators parallelly, that is synchronously at a time. and depending on the value of V in, the output of this comparator will be set 1 or 0 or something like that. And based on the output of this comparator, this priority encoder will work and it will encode this entire combination into its equivalent 3-bit digital output. So this is how it works. Now, in some cases, in some books, you might find that this R and this R, these are replaced by R by 2 and R by 2. So, if this is replaced by R by 2, then what will be the reference voltage at this point? It will be simply VR by 14. See, here that will be VR divided by 7R, but the voltage drop is across R by 2 now, so R by 2 is multiplied. So total V reference would be VR by 14. And in this way, if we proceed, we will find this one 3 VR by 14, this one 5 VR by 14, and so on. But here in present case, we have used, here the value is R, here the value is R. So we are getting this typical VR by 8, 2 VR by 8, 3 VR by 8, etc. Again, if we want to design it in such a way that here instead of using R, we are using a 3R by 2, and here instead of using R, we are using R by 2, that is the green column now. So here, if we calculate, you will find that the reference voltage here would be VR by 16, then 3 VR by 16, 5 VR by 16, and so on. So if we take the previous example, that is V reference, suppose this V reference is 8. So if V reference is 8 in the previous circuit, that is when this is R, this is also R. The corresponding V reference will be VR by 8 at this point. That means it will be 1 volt. So if we see, if we try to draw a graph, the digital output, you see here, the digital output. Here from 0 to 1, it will be 0, 0, 0, this one. At the 1, it is actually jumping to the next level. Why? Because here the reference voltage is 1, but here the next level is actually 2. Here VR is we are giving VR as 8, so 8, 8 getting cancelled, and we are getting 2. The next range is 3. So the jump or the moving from this stage to this stage to this stage, it is happening at 1 volt interval over here. So that is why here we are getting this black curve like this. And ultimately when it reaches to 8, it will come down. But in case of this combination, that is when this one is 3R by 2 and this one is R by 2, we have already calculated that in this case, the reference voltage will be VR by 16, then 3 VR by 16, then 5 VR by 16, and so on. So if here you put the value R as V reference, not R, sorry, 8 as V reference, so the starting value would be 0.5. That is, the V in will go to the next level when it is greater than 0.5 volt. But the difference between these two voltages is 1. 3 VR by 16 minus VR by 16, if you calculate it, you will find the difference between two successive voltage level is 1 volt. But the starting value would be different. That will start from 0.5 volt. So here, from when it is crossing this 0.5, it will jump to the next step, that is 0, 0, 1. Then after 1 volt interval, again it will jump. So at 1.5, it is jumping from 001 to 010, and so on it will go. Now, at the last range, when it is greater than 13 VR by 16 but less than this V reference, that actually increases the length of this particular level. That is, it starts from 6.5 and it is ending at 8. While the first level has been shrinked from 1 volt to just 0.5 volt. So here it is just 0.5 and here it is 1.5. So a bit of asymmetricity is happening in this kind of design. But here, each of these intermediate levels, the length of this, if we want to call it, or maybe the step height, it remains one volt. So if we study these two waveforms side by side, it will be something like this. While we are using only the value of R, it will give us this black curve, and while we are using this 3R by 2 and R by 2 combination, we are getting this green curve. So basically, these are actually converting the analog signal into the corresponding digital output, only the starting value here is different. As if this green value is shifted a bit in this direction. So that is the difference. Now here again, if we design it like this, here R by 2 and R by 2, then if we use the same V reference value, that is 8, we will get the difference between these two successive levels in a fraction. It won't be a whole number like 1 volt or not whole number. Here also we are getting fraction, but it's only the starting value. But here the successive level difference, we will be getting a fraction value. So in this way, depending on our need or depending on the desire of the designer, these levels can be set and the step heights can be increased or decreased, or if we want to shift it a bit like this or shift it in this direction, that can be done using various combinations of resistance. But we have to keep in mind that at least we need some equispaced range. Maybe we can shift the start value by altering this two resistor value, but it will be better to keep an equispaced analog voltage levels or equispaced voltage reference, so that we can actually track the analog signal in a proper manner. Otherwise it will be a conversion, but that won't be a very accurate one. Now there is a term which is called quantum level or Q. This quantum level is nothing but the difference between two successive voltage levels or two successive voltage reference. So here in this case, this red one, here it is, you see, if you find the difference, it will be VR by 7. Here in this blue color, here you will find it VR by 8, and so on. So in some books, you will find the design is like this R by 2, R by 2. In some books, you might find that the design is like 3R by 2 here and R by 2 here. And in some books, you can find all the resistor value are chosen as R. So all of them are correct depending on the what kind of output waveform you want to generate. Now, in this particular case, two most important things we can observe from here. One is the conversion time that we are going to talk about. Another one is circuit complexity. Now, circuit complexity means how many number of complex circuit elements have been used in design this whole ADC. So you can see that for just 3-bit ADC, to design 3-bit ADC, we need 7 number of comparators, 1 latch, 1 priority encoder. So there are a lot many number of circuit elements that we have been used. A lot more number of comparators especially. So obviously that will increase the circuit complexity, and obviously it will increase the corresponding delay, it will affect the speed of the circuit and so on. Because there is a delay from this input to output, and in latch it will suffer some delay. In converter from input to output, it will suffer some delay. So our aim would be to decrease the circuit complexity, or mainly we are going to focus on decreasing the number of comparators here, the number of these op-amps here. But here the main advantage of this is every comparison, all the comparisons have been done parallelly, and only one clock signal is needed to translate this whole thing to the output. So just one clock pulse. So this is the fastest of rest of the ADCs. So that is why it is alternatively called as the flash ADC. That is, in a flash, the input value is converted or is going to the output value. So hence it is called the flash ADC. So our next approach would be the conversion time. We are very satisfied of that, but the circuit complexity, we are not very satisfied with this kind of ADC. So in next approach, we will try to decrease the circuit complexity. Here comes the counter type ADC. So what was our main goal? Our main goal was to decrease the number of comparators. So here you can see counter type means, obviously it has got something to do with counter. Here only one comparator is used. This is the circuit schematic of a counter type ADC. Only one comparator has been used. Here also comparison is done, but using one comparator. A gate we are seeing here, and here an up counter has been used. Now basically the output of this counter should be compared with the input voltage, and depending on that the output should be generated, but this output is digital output. Now digital output cannot be directly compared with the analog input, right? Here also in previous cases we have introduced an analog signal, or we have created some analog reference voltages that has to be compared with the input voltage. So here also we have to make sure that this input analog voltage should be compared with some analog voltage or analog reference voltage. Here comes the significance of using DAC here. So here, to produce or to design this ADC, we need a corresponding DAC. What is the purpose of this DAC? This DAC is actually converting the output of this counter into the corresponding analog signal, and that analog signal is compared with this Vin. And depending whether Vin is greater or Vin is less than the then this analog voltage or this reference voltage here, the output of the comparator will be either 0 or 1. So let's see how it is happening. At first, the counter is set to 0000. That is, it is cleared to 0000. Now, suppose this DAC has got a resolution of 1 volt, maybe. So now this 000, the analog voltage output would be 0 volt. And this 0 volt is compared to this Vin now. Sorry, the analog voltage is here, suppose it is 1 volt. Now this is compared with this Vin. If Vin is less than this 0, this analog input voltage over here, it is less than this, the output would be 0. But if it is greater than this value, the output will be 1. Suppose it is greater. So the output is here, we are getting 1. Now this is actually one of the input terminals of this AND gate. That means when it is 1, whatever be the signal of this terminal, it will go to the counter. And here this terminal, this input of the AND signal is getting the clock signal. That is the train of pulses. So here the output is 1. At the output of this AND gate, we are getting the clock signal. So the counter is getting the clock signal. So when the counter is getting the next clock signal, it is 1, it is getting the clock pulse. It will increase its count from 0000 to 0001. And this 0001 is now getting converted to its equivalent analog output. And that analog output is now compared with, suppose this is A. This analog output is now getting compared with this Vin. So if Vin is greater than this, then output will be 1. It will continue getting the clock pulses because It is 1 means the clock pulse is appearing at the output of this AND gate. The clock pulse is going at the input of this counter. So the counter is getting the clock pulses, it will increase its count. In this way, the whole system is going to work. Now, as soon as this analog voltage becomes greater than this V input, the output will become 0. As soon as it becomes 0, the output of this AND gate will become 0 and the counter won't get any clock pulses. So the counter will stop counting and that corresponding output will be the output of this particular analog voltage. So if we see this graph, suppose this is the analog voltage level. Now, after the first clock pulse, the counter is the DAC is producing the voltage which is equivalent to this level. So this is less than V in, this is less than V in. So at the output of this comparator we are getting 1 and that means the counter is getting the clock pulse, so it will increase its count to this value. Again this value is again it is less than V in. So the output is 1, the clock pulse is generated or the clock pulse is fed to the counter, it increases, it counts to this level. Here also it is less than V in, again it will increase its count to this level. Again this is less than V in, it will increase its count to this level. Now as soon as, that is after the 5th clock pulse, it is crossing the analog, the input voltage, that at 5th clock pulse, the input voltage is less than this one. So at that point, the output of the comparator will be 0. And the output of this AND gate will be 0 and the counter won't get the clock pulse. It will stop counting at this 5. Not at this 5, it will stop counting at this way. This pulse, after this pulse, that is after 6. So the corresponding digital output will be 0, 1, 1, 0. This one. So here we are seeing that until and unless it detects this analog level, or alternatively until and unless this input, this reference voltage is crossing the V input, the counter will continue counting. As soon as this reference voltage becomes greater than V in, it will stop counting. So basically, how many number of clock pulses will be needed actually depends on the value of this V in. If V in this level, suppose this is the value of V in that case, 1, 2, 3, 4. 4 number of clock pulses will be needed in order to produce the corresponding output, the digital output. Here, 6 number of clock pulses will be needed. Now, if it go beyond this and V in now here, then it will need 7, 8 clock pulses, total 8 clock pulses. So, basically the conversion time here is variable. We cannot predict the conversion time initially, that we can actually take the data after a fixed number of interval, after a fixed interval of time. It is not possible here because it totally depends on this V input or the value of this V input. So the conversion time is variable. But what will be the maximum conversion time over here? Suppose at the last count, that is in present case, the counter is a 4-bit counter. Digital output that we are generating is 4-bit digital outputs. So here, if V in value is such that at the last count, that is when the output here is 1, 1, 1, 1, that is after 15th clock pulse, it actually crosses the V in value. Then the conversion time would be 15 in case of 4-bit DAC or 4-bit counter output. So the maximum conversion time will remain something like 2 to the power n minus 1. Here the total number of bits of this counter is 4, so 2 to the power 4 minus 1, that would be 15. So it might be less than this 2 to the power n minus 1, but it can be equal to 2 to the power n minus 1. Maximum conversion time can be this many number of clock pulses, and that is certainly a lot many number of clock pulses compared to the previous one. In previous one, only one clock pulse was needed, but here this 2 to the power n minus 1 clock pulse is needed. Not only that, we have gotten a variable conversion time. It is dependent on the input value. Also, if we increase the number of bits, and by increasing the number of bit means we are basically introducing more levels to a specific range. Within a specific range, we are introducing more discrete levels. That is, we are actually more fine tuning the entire analog signal detection. Or another way to say that, we are decreasing the step height. So here, if we just simply double the output of this counter, the output will be something like this. It may be something like this. So this digital output is more fine compared to this one. I'm zooming it like this. Suppose this is there. Now we are introducing more number of discrete levels. So now the step height has been reduced, and if we now try to reconstruct this analog voltage, it will be something like that instead of this one. Like this. This will be a lot more approximated than this one. So more the number of bits or more the number of levels here, more will be the accuracy. That is, more accurately we can actually convert this input analog signal into its corresponding digital one. But here, as we increase the number of bits, that means basically we are increasing the maximum conversion time, because here conversion time is dependent on the number of bits over here, in addition with the input voltage value. So these two are the drawbacks. Although the number of comparators have been reduced in this case, but the conversion time or the maximum conversion time here is increased to a great degree. So that is one of the disadvantages. Now another disadvantages would be something like this. If the analog signal is varying very rapidly, that is, instead of having a slow pace, suppose it is varying like this. Here, a sharp variation is happening at this point, maybe at this point. So here you see the counter starts counting from 000, that is from this value, and it needs a certain amount of time or a certain number of clock pulse to first detect that analog signal. Once it detects the analog signal, the counter again is cleared, it drops down here, again it will start counting like this. So if some kind of change or some kind of sharp variation like shown here has taken place in this time or in this time, it won't be able to be detected by this kind of ADC or this kind of analog to digital converter. So here, if the change is like here, or maybe alternatively, instead of this, suppose it is like this. So these changes, it won't be getting detected. So some portion or a large portion of the analog signal is actually getting left out. So this is another problem. We cannot very accurately detect the analog signal if we simply use this counter type ADC. So we need some kind of modification in order to detect this in order to detect this particular variation. So we can do one thing. Basically, we can decrease the search time and we can keep the this many number of clock pulses for once. That means we only need to detect this signal for one time. And once the signal has been detected, that is, once the V reference voltage crosses the V input voltage, it won't getting cleared again. It won't drop down to zero again. Instead, it will now track this entire signal. So that bit of modification needs to be done in this present circuit. So that can be done if we replace this simple up counter by an up down counter. So if we use an up down counter, what is happening? The philosophy remains same. Only here the output of this comparator is going to the input, one of the inputs of this AND gate, and other input is fed to the clock. The clock signal is given to the other input, but here it will actually be fed to a controlling block or to a switch. It will actually, the output of the comparator will actually goes to a switch or to a control block. The output 0 or 1 will actually have some kind of significance. That is, when the output is 0, it will down count, and when the output is 1, it will up count. So when it is actually tracking it for the first time, as you can see, over here, it is it has it has tracked this V input at this particular voltage, at this particular point, at this particular clock pulse. So here the output of the comparator, will become 0. When the output of the comparator will become 0, then it will start down counting. It is going below. Again, after the down counting, this analog voltage is less than this input voltage. So again, the output will be 1 and it will again up count. So again, it will be up counting like this. On the second stage, this voltage level is greater than this V in. So again, it will down count. This level. Now, this level is less than V input. It will do the up count. Here, after this one jump towards the higher value, again it will remain below this V in. So it will continue this up counting. Once it is crossing this V in, then it will again down count. So here you see, we don't need to reset the entire counter value to 0000 and start counting from this one again. Here, once we have detected the signal, now the job is to track that signal like this. So here the missing out portion is much less compared to the previous design. So here also, if we want to track this signal, after it crosses this, it will go a down counting here. So here it is less, then again it will go up counting. It will again fall to down counting. It will less, it will again up counting. So in this way, it will continue to track this, and at this point, it will be able to track these sharp changes, or if some changes happening here, it will be able to detect this change. So that is why this entire ADC or tracking type ADC is working. Since it is tracking the signal, the name is given as the tracking type ADC. But here also, the maximum number of conversion time, the maximum conversion time or the maximum number of clock pulses will remain 2 to the power n minus 1. Why 2 to the power n minus 1? Because for the first time, if we want to detect it, for the first time, it might cross this viewing value at the maximum count of this particular counter. So the maximum conversion time will remain same 2 to the power n minus 1, and the dependency of this conversion time on the input voltage value, that also remains same. Only this problem that has been taking place in counter type ADC, that is this missing out portion, that problem that has been reduced to a great degree. So that is why from here, from this design, we actually modified this counter into an up down counter. But when we are modifying this that previous up counter to up down counter, obviously we are increasing the circuitry element within it, and that's why it will increase the circuit complexity compared to the previous counter type ADC. So if we know that whatever we are going to convert in the digital signal, that analog signal is very slow varying, is not any there are no rapid changes or no spurious changes in between these uh, in this analog signal, then we would stick to this counter type ADC. Otherwise, if the signal is very rapidly changing, some unpredictable change might occur that we are assuming that it may occur. In that case, we will just modify the design with this up down binary counter. We will modify the up counter and replace it with up down counter. So we are actually increasing the circuit complexity a bit, but we will be able to track the entire analog signal more accurately. It increases the accuracy at the cost of circuit complexity. But still here, the number of comparators will remains less compared to the first type, that is the parallel comparator type ADC. It remains lesser. So circuit complexity is lesser than that of the flash ADC one, but it is greater than the counter type ADC one. Now here, this counter type ADC is also called a single slope type ADC. Why? Because if you study this waveform, you will see that to detect the input signal, it will actually growing in the positive direction. So as if it is approximated, if it is approximated as a straight line, it has got a positive slope. So that is why, and it's a single slope, not in both direction. That is not like this, but it is just rising in this direction only. So creating a single slope with this axis. So that is why alternatively it is called a single slope ADC. So এই তিনটের মধ্যে কোনো যদি প্রবলেম থাকে, কোনো জায়গা যদি আরেকবার করে রিপিট করতে হয়, then tell me, I will do that. Any confusion or anything? এই তিনটে টাইপ এডিসির মধ্যে anyone? কানেক্টেড আছি তো?
Yes, ma'am. Connected আছে.
ওকে, তো এটার কোনো জায়গা, কোনো পোর্শন ইউ ওয়ান্ট মি টু রিপিট? Okay, I think it is clear then. Fine. Okay. Now the next one is coming as the successive approximation type ADC. Now, what is successive approximation type ADC? Here, the entire counter block, like in the previous case, which was like an up-down counter for tracking type ADC, and just an up counter in case of the counter type ADC, that block is replaced by something which is called as SAR, or successive approximation register. Now, before going into the circuit schematic of this successive approximation type ADC, let us try to understand the philosophy of this entire successive approximation type ADC, that is SA type ADC. Here, what is done? So, in previous cases, our main problem was maximum conversion time, which was 2 to the power n minus 1. So, if we increase the number of bits, that is, if we increase the fine tuning or the accuracy, we have to sacrifice this maximum conversion time. Also, another one is that the conversion time is variable and is a function of input voltage. Whatever be the value of the input voltage, depending on that, the number of clock pulses or the time of conversion will be needed. So here we want to mitigate these two problems. We want to reduce obviously the maximum conversion time, and we want to get rid of this dependency. That is, we want to measure the output at fixed interval of time. That will be easier. So here, successive approximation type ADC. So it has to do with some kind of successive approximation or successive comparison. So the basic philosophy is, suppose we have got a total range of this many. This is suppose Vx. Okay. Now the analog voltage Vin is given. So here also we will use the comparator, that is, comparison has to be done. Comparison has to be done. But the method of this comparison will be a little bit different. The entire range, suppose it is 0, suppose it is Vx. The entire range at first, it will be divided into Vx by 2. That is exactly, it will be divided in two portions. That is 0 to Vx by 2 and Vx by 2 to Vx, these two ranges. Now we will try to see whether this Vin is falling in this upper range or this Vin is falling in this lower range. Basically what we are doing, we are comparing this Vin with this Vx by 2. Okay. Suppose the Vin is falling at the lower range, at this range, that is, its value is less than Vx by 2. So it will fall in this range. In that case, we will discard this whole upper range. On next step, what we will do, now the existing range would be 0 to Vx by 2. So now we will divide this range. We will divide this range into two parts, the upper half and the lower half. This range means Vx by 2, that is now divided by 2. And we will compare this Vn with this Vx by 2, and we will see whether this Vn is falling in this range or the Vn is falling in this range. If Vn is falling in this upper range, suppose, then this entire range, lower range, will be discarded. Only this will remain. Now in the next step, this is actually the valid range now. So we can see with each step, the width of the entire range is getting decreased, and it is become closer to this Vin value. So now again this range will be divided into two parts, and again we will see whether falling it will fall in this range or in this range. In this way the whole comparison will take place. So this is the basic philosophy. Now for how many number of times this uh, dividing of or this division of this range will happen, that we will see. But the basic principle is this, that is whatever be the range, divide it by 2 and compare it with v in value to see whether v in is greater than that particular midpoint value or less than that particular midpoint value. If it is greater than the particular midpoint value, then the corresponding range, that is here in this case the upper range will exist, and we will discard all the values in the lower range.